There we go. All right. Let's go ahead and get started today. Let's start with one more example of oxidation numbers in practice. How about we do let's do this one. Let's see what let's see what the agents are for this one. That's a weird sound. She like quacked. Alrighty, let's see. Good morning. So, coffee first, right? If we want to look at this reaction, if we want to figure out what the oxidizing agent and reducing agents are, what we want to do is take a look at the oxidation numbers for each species in this reaction. This reaction is a bit more, it's not one of our kind of classic reactions that we talk about because this one involves more than just a couple of things happening. So you would, of course, not be expected to predict the products for this or anything like that. So, alrighty. So let's go ahead and take a look here. Hopefully a couple of these we can go right off the bat with. For example, this copper, hopefully we can tell is 0. Remember, because it's by itself, anything by itself should have an oxidation number of 0. Our water we did yesterday, so hopefully we remember that one. We have done technically the nitrate ion, but maybe we should just do those again just to practice. So let's take a look at HNO3. We know that this is as a compound. We have to make sure that all of our oxidation numbers add up to 0. We have rules for hydrogen and oxygen, which means we're solving for nitrogen. Well, Oz is, hold on, apparently he's going to just do this until I let him in. Oz, come in here. Come on. There you go. It's always when I'm over here that they all have new habits that I have to deal with. If you solve this for n, you get +5. Alright. So, we're good with nitric acid now. In a polyatomic ion, remember the oxidation numbers don't change, so we have nitrate on the right side as well. So that nitrate we know is going to be the same oxidation numbers. +5, -2, +1. And then we can tell, since the copper 2 nitrate is an ionic compound, we can tell that we have a copper in the 2+ oxidation state. Hence it's copper 2, right? And so we just have one more left. We have the nitrogen dioxide over there. So we know that nitrogen plus 2 oxygens must equal 0. So nitrogen plus 2 times -2 equals 0. Remember, oxygen being more electronegative, we're going to deal with it first because it's more electronegative than nitrogen is. We get nitrogen to be +4 here. So if we go ahead and indicate that, make that a little bit more clear. Okay. And so now we can go ahead and take a look at all of this. So we have a lot of elements going on here. We have our reactants and products. We have copper, nitrogen, hydrogen, nitrogen, and oxygen here. We started with copper 0, it became +2. Hydrogen looks like it stays +1. Nitrogen looks like on the left we have +5, on the right we have +5 and +4. And then oxygen we have -2, -2, -2, -2. So all of the oxygens are still at -2. So notice we have, in this reaction, we have nitrogen with two different oxidation states because they're in different compounds in the reaction, which is okay. So, but however, we can see that we do have a change from +5 to +4 and from 0 to +2. We see that the copper is being oxidized, it's losing electrons, and the nitrogen will be gaining them, so the nitrogen is reduced. And so, because the copper is oxidized, remember that makes it the reducing agent. And since the nitrogen is reduced, we have to go and look at our chemical equation. We find the component that has the nitrogen in it in the reactants, and that's the nitric acid. So that tells us that nitric acid is the oxidizing agent. And we're done with our problem. Any questions on that one? So it's really the same process we do. We just have to figure out the oxidation numbers. Most often we do the kind of little algebra here to figure them out. And once we have them, we can kind of take a look at them, see what's changing over the course of the reaction, and then identify what's happening there. All right? Cool. So then, we are going to then move on to chapter 10. There are 11 chapters, of course, so we are almost done. This one has a fun title, Stoichiometry. We will see what this means as we go through. And typically how I like to explain this is kind of using cooking analogies. So the chemical reactions we've looked at so far kind of give us recipes. And so, say for example, we have something like this. We have calcium chloride and sodium sulfate. Producing sodium chloride and calcium sulfate in a double displacement reaction. What this reaction tells us is that we can put together kind of equal amounts of our reactants because they have the same reaction coefficient, and we'll get out 2 parts of sodium chloride and 1 part of calcium sulfate. If we take a look at this in a different light, if we say we're going to take 2 pieces of bread plus 3 pieces of lettuce plus 1 tomato, and we're going to make a sandwich, it's going to be kind of the same thing. So a recipe like this, we're going to take some reactants, make them into a product. It's going to be just like a chemical equation. So we're going to take some reactants, whatever those may be, we're going to come out with some products, and they're going to come in these kind of predefined ratios. So we know we need to combine all of these things in the reactants in those amounts to get our product out. Just like in the previous equation with the calcium chloride, we need to put 1 part calcium chloride with 1 part of sodium sulfate. We get out 2 parts of sodium chloride and 1 part of calcium sulfate. If we want to think about it in terms of a cooking recipe, we put in 2 parts of bread, 3 parts of lettuce, 1 part of tomato, and look, now we have a sandwich. 1 sandwich. And this is going to be valuable because we can say, okay, well, how much do I need to make 4 sandwiches? We can figure this out. Well, so we know that we have 2 bread, or rather, we have 1 sandwich for every 2 bread that we have. Actually, no, I did it. I did it correctly. Why did I erase that? We have 2 pieces of bread in every sandwich, right? And so we're going to see that this is going to be just a unit conversion, like always. So we're going to see that in order to make 4 sandwiches, we would need 8 pieces of bread. Notice, as always, our sandwiches cancel out, and we're left with bread. That's the unit we want. If we want to do it for lettuce, we know we want 4 sandwiches. This time we know we need 3 lettuce pieces for every sandwich. And so we're going to need 12 pieces of lettuce. Again, noting that our sandwiches cancel out. And the last one, we have the tomato. There we go. And so we're going to need 4 tomato slices or whatever. And so this tells us exactly what we need to make that amount of product that we're looking to make. And we're going to see this is exactly the same process for chemistry. So we would need to put all this together to make those 4 sandwiches. And this is something that hopefully you can, I mean, at least right now, this is stuff that is not terribly confusing. You know that if you want to double a recipe, you want to double the yield of your recipe, you would just double all of the ingredients, and you would just be able to do that. And so, by the way, we did cancel out our sandwiches here. And so it's much the same process. We can see in a different situation, or if we take our calcium chloride, let's take another, let's do another reaction actually. Let's do this one. So if I want, let's say 16 molecules of ammonia, how many molecules of nitrogen and hydrogen will I need to do this? So our chemical reaction will tell us the ratios that we need to put together in order to get our product. So we know we want 16 ammonias. we know that if we put in one nitrogen, we get out two ammonias. Those are our reaction coefficients. And so we will need to put in 8 ammonia molecules, or 8 nitrogen molecules. If we wanted to figure out for hydrogen, we see in our reaction we have a coefficient of 3 for hydrogen. So we have 3 hydrogens here to make 2 ammonias. And so that's going to be 24 hydrogens. Notice, as always, with any unit conversion, you have your denominator canceling out with your starting quantity, and you are left with the desired quantity. All right, if we do this again, let's see. Let's do it again. With the same reaction, let's take a look at it in another light. So let's say I have 36 hydrogen molecules, and I want to see how much I can make of the ammonia. So we have 36 hydrogens. We're going to look at our reaction. We see the coefficient of hydrogen is 3. So we're going to put 3 down here. And then we're asking how much ammonia can we make. So let's go ahead and see what ammonia's coefficient is. It's 2. And so that tells us that we can make 24 ammonia molecules using those 36 hydrogen molecules. And if we wanted to see how much nitrogen we would need, well, we just go up to our reaction. It says we have a coefficient of 1 for our nitrogen. And so that tells us we need 12 nitrogens to be combined with those hydrogens to make the 24 ammonias. All right, so hopefully nothing too crazy here. What's important here is that reaction coefficients tell us the ratio of each reactant to each product, or to each other. So if we have another reaction, let's say we have, how about we have the decomposition of hydrogen peroxide, we're going to get out a couple of conversion factors here. This tells us that we have 2 hydrogen peroxides equals 1 oxygen, and 2 hydrogen peroxides equals 2 waters, and then we also get 1 oxygen equals 2 waters. So we get out 3 conversion factors from this using the reaction coefficients. So the 2, the 1, and the 2 will tell us the ratios that we need to put things together to make whatever product, or in this case we have just one reactant, but making multiple products. And so it turns out that these While they are true for just molecules, it's kind of silly to talk about molecules since they're so small and they weigh so very little. We're going to see that this is the same as saying the mole ratios between them. So we know two hydrogen peroxide molecules will give us one oxygen molecule. 2 moles of hydrogen peroxide molecules will give us 1 mole of oxygen molecules. Say dozen instead, it works all the same. 2 dozen hydrogen peroxides give us 1 dozen oxygens. And so it's all the same here. We also get 2 mole H2O2 equals 2 moles of water for use as conversion factor. And then finally 1 mole of oxygen equals 2 moles of water. And so let's take a look at this. If I have (3.62 moles of hydrogen peroxide), how many moles of oxygen do I get? Okay, so our reaction is here. We're going to want to look at the reaction coefficients and use those to go ahead and figure this out. So we're going to start with our given quantity. We're looking for oxygen, so oxygen is going to go on the top. We have hydrogen peroxide, so that's going to go on the bottom. We're using, right now we're using this relationship. It's the reaction coefficients for those substances. We do this math and we get, oh, actually I can do this one in my head, hooray. So we're going to get out 1.81 moles of oxygen by decomposing that amount of hydrogen peroxide. All right, so hopefully nothing terribly crazy here. But this is a very important kind of concept here, where this chapter, by the way, is really nothing new for us. It's just going to be combining a lot of different concepts that we've already learned in a kind of new way. So the whole point of this chapter is that we are learning to use our reaction coefficients to convert between moles of one thing and moles of another thing. That's the whole point of studying these chemical reactions and balancing them and doing all that stuff, is to figure out these reaction coefficients so that we can actually put them to use. Because in chemistry we want to say, okay, well, I want to make this amount of whatever. How much do I need to make it? You know, and so we'll see that if we know the moles of one, we can use our reaction coefficients to figure out the moles of any other substance. And hopefully, we might remember a few ways to get moles from other measured quantities. For example, if we had grams of A how might we go from grams of A to moles of A? Do we remember how to do that? We have a special conversion between those two. Maybe you remember that is the molar mass of A will get us between grams and moles. And if we wanted grams of B, Well, we would just use the molar mass of B, right? I'll go away, it's a phone call. Whatever B happens to be. Let's take a look at this. This should, it's really going to be nothing new. I'm going to just leave a little bit of space here. But let's say, here's a reaction for us. Combination reaction. A redox combination reaction. If I react 16.24 grams of sodium, how many grams of sodium chloride can I make? Well, if we're starting with grams, we have to remember that the only way to go from one substance to another substance in chemistry is to use reaction coefficients, to go between moles. That's it. That's the only way you can do it. You can never go between grams and grams. It doesn't work that way. We have to go between moles. So we know, if we kind of want to plan this out, we know we're going to have moles of sodium to moles of sodium chloride in here. That's the only way we can switch between substances in our kind of math here. And since we're not given moles of sodium to start, we're given grams, we do know how to go from grams to moles. And since the question asked us for grams at the end, we can do that as well. Notice we have three conversions we're going to do here. The one we're going to use here is the molar mass of sodium. And on the other side, we're going to be using the molar mass of sodium chloride, since that's our substance B. And remember, anytime you're switching between substances, we need to use our reaction coefficients as the third conversion factor there. All right, so let's go ahead and see what this would look like. So let's start with our quantity of sodium. Our first conversion factor that we've noted here is we're going to be using the molar mass of sodium, which if we look it up is 22.99 grams of sodium for every mole of sodium. We want to now use our reaction coefficients, so let's just scroll up. It looks like both of them have a coefficient of 2. So we're going to write those in here. And then we're going to have our last one, which was the molar mass of sodium chloride. This is 58.44 grams per mole. And this is going to be grams of sodium chloride, moles of sodium chloride. Notice, whenever we're doing a unit conversion, we should always check to make sure our units are canceling out. We have grams of sodium cancels with grams of sodium. Moles of sodium cancels with moles of sodium. Moles sodium chloride cancels with moles sodium chloride. We're left with grams of sodium chloride, which is what we're looking for. And so, if we do this calculation, where did I put my calculator? Bust out your friend. Always do this along with me. 16.24 divided by 22.99 times 58.44. We do this and we get 41.28 grams of sodium chloride. Our sig figs here, we're going to just keep 4. That's what we started with in our original problem. We're going to just keep our sig figs here. And so we are done with this one. All right, any questions on that one? All right, let's see what else we can do with this idea. Well, let's say maybe since I might be doing a reaction in solution, maybe I don't have grams of B that I could isolate very easily, but maybe I'll end up with a solution. And maybe I want to see, okay, well, what can we do with this? Well, we're going to see that we have, actually, let's do it with A first. Let's do it with A, and then we'll worry about B. We'll just make this a little bit easier, I think. Do we remember how to go between volume of a solution and moles? Hopefully we do, maybe. Remember that's something called molarity. So, okay, well, let's go ahead and see this as an example. So let's say in the same reaction, if I have 100 milliliters of some aqueous chlorine, we can start, instead of starting with grams, what we can do is start with solution stuff. So we're really, again, this chapter is just going to be taking all the various ways we know how to get moles, and we just are putting them all together. So we know for any calculation like this, we are going from moles of what we're starting with to moles of what we're being asked for. Oh, I guess I need to give you a unit for sodium. What we can do with this, since I'm asking for grams of sodium here, that's the unit we want to end with. And if we need moles of chlorine at some point, we're going to have to figure that out. It looks like we do have a solution here of chlorine. So what we're going to do is we're going to start with our volume, specifically in liters of chlorine. Actually, move that a little bit closer. 2 moles of chlorine. Remember, we can do that from a volume of solution. But notice we're given milliliters to start, so we just need to adjust that real quick to liters, right? Because molarity is between liters and moles, right? So if we're given milliliters, we need to convert it to liters. These are our reaction coefficients. If we're going from moles to grams, that's our molar mass. And hopefully this first one is just a metric conversion, right? So this time we have 4 things to do. And again, we kind of just start by remembering that we need that mole to mole thing in the middle, and we can kind of branch off from either side to figure out where we want to go and where we're starting from. So let's do it. We have 100 ml to start. We're going to want to convert that into liters. I'm going to make this just a little bit smaller. Oops. That's the way I've done it for you guys. Alright, so hopefully the metric part is not too bad. Next, we're going to want to use the molarity. That's what we've planned out here. So we know that we have 0.750 moles per liter. That's what molarity means, moles per liter. We have our reaction coefficients. Hearing one of them eating something, but I don't see them. Oh well. And then our last one, it's according to our plan, is we're going to use the molar mass of sodium, which was 22.99 grams for 1 mole. And I always like to make sure that I write the substance as well, so that I know exactly kind of what things I'm working with at each time. So let's double check everything cancels out. So we have milliliters canceling with milliliters, liters canceling. Now we can cancel our chlorine. We have moles of chlorine canceling with moles of chlorine, moles of sodium with moles of sodium. We are left with grams of sodium. That's what we want. And so now we can go ahead and plug it all in. So 0.1 times 0.750 times 2 times 22.99. Doing all this, we're going to need to react. Oops. How many things we have? It looks like overall we're going to have 3 sig figs here. So we're going to want 3.45 grams of sodium to react with this amount of chlorine. So just notice we have our sig figs there. Just don't forget those. Hooray! Questions on that one? So again, these are just unit conversion problems over and over again. Alrighty, how about this one? Now let's do one with how about the volume of solution B using its molarity. Let's do one of those. Alright, how about we do this one? Alrighty, let's take, what reaction shall we do? How about we do, let's, that equals. Do I want to do this one for you guys? Why not? Okay, if I want to make 2.250 molar phosphoric acid, how many ml of this can I make with, I don't know, 25.6 grams of tetraphosphorus decoxide? Let me go look up its elements real quick. Alrighty, so if we do this, okay, there it is. Oh, I didn't balance this for you guys, did I? We do get 6 and 4. Yes, those are the coefficients for that. So, if we go ahead and work with this, well, always let's start with what we have. Our mole ratio in the middle. So we're looking for milliliters of phosphoric acid. We can't go from moles to milliliters right away, but we can go from moles to liters, right? And then from liters to milliliters. And it looks like we're starting with grams of P4O10. And we can go from grams to moles directly, right? So if we want to look at what conversion factors we're going to need this time, we're going to need our molar mass, because we're going from grams to moles. Always, we have our reaction coefficients in the middle. Going from moles to liters, that's the molarity of our phosphoric acid. And then this last one is just a metric conversion at the end. Alright, so let's go ahead and take a look at this. So, we're going to start with our 25.6 grams. I have looked up the molar mass because I am too lazy to calculate it, 283.9. And I will write down that I'm using P4O10 for all of these. So that's our first one. The second conversion we have, the dark blue says reaction coefficients. So we see that we have 1 P4O10 and 4 phosphoric acids. Putting P4O10 on the bottom to cancel it out. Next, our next conversion is going to be the molarity of the phosphoric acid. It says we are looking for 0.25 molar. So remember, that's moles per liter. Since we want moles on the bottom, liters is going to go on top. And then we just have our metric conversion on the top, or next, just to go from liters to milliliters. And now we can go ahead and solve this, but let's go ahead and double check. Grams of P4O10 cancels out. Moles cancels out. Moles of phosphoric acid. Liters cancel out. We'll be left with milliliters of phosphoric acid, which is what we're asked for in the problem. So here we go. 25.6 divided by 283.9 times 4 divided by 0.25. So I guess just cancel that out anyway. Times 1,000. We get 1,442 0.76 milliliters, which we're going to go ahead and round this to, looks like 3 sig figs here, so 1,440 ml is what we're going to end up getting out at the end. Hooray, we did it! So, this whole chapter, again, we're going to be going from some quantity of substance A, turning it into some quantity of substance B. In the middle, we have our reaction coefficients. That's the entire thing about this chapter. So, if we scroll up though, I have left some space because we do have one last kind of bit here that we can talk about. Perhaps we remember we have gases too we can deal with. So we can deal with any sort of pure substance, so solid, liquid, or gas, we can do grams of. We can take a solution volume, or we can deal with gas quantities. And hopefully we remember our ideal gas law will tell us how to go between moles and all of those other quantities. So we can go any pathway we like. We can, let's do an example. Okay, here we go. Example time. How about we do let's take some magnesium and burn it. Let's do it. If I have 0.942 atmospheres of oxygen at 500 Kelvin in a 10-liter container, how much magnesium can I react with? You thought you were done with all these pesky gas laws and that sort of thing, didn't you? But there's no escape. So, unfortunately. So, we must always do this fun stuff. So, in the middle, moles of oxygen to moles of magnesium. Notice I could also ask you how much magnesium oxide I get out. You know, it doesn't matter. I could ask you about reactants or products. The process is exactly the same. If I want grams of magnesium at the end, we can go directly there. And if we wanted to figure out moles of oxygen, well, we know we have our gas quantities here. And so, of course, in the middle are reaction coefficients. The last one, we need the molar mass, because we're going from grams to moles. And then we'll use our ideal gas law for the first one. Lots of fun stuff here, isn't it? But the whole point of this is I can do all sorts of crazy things with these. If I wanted, I could figure out how much solution the magnesium oxide can make or something. I could go crazy with this. Alrighty, so let's do it. So we know that N equals PV over RT. So we can go have moles directly. So if we do that, we have a pressure of 0.942 atmospheres times V, which was 10 liters, R, and then the temperature was what, 500 Kelvin? My God, these horrible big follows people, they're here every day. Go away. I'll have to like figure out how to block big follows or something. Alright, so that'll give us moles of oxygen, right? If we do all this fun stuff, we can now continue on. Our reaction tells us we have 1 mole of oxygen to give us 2 moles of magnesium. And then our molar mass of magnesium was at 24.3. Let's find out. 24.31. Okay. Yeah. All right, we can do all this fun stuff. Notice, let's make sure everything cancels out as always. Atmospheres will cancel, liters will cancel, Kelvin cancels. We're left with moles oxygen down there, which will cancel out here. Cancel out moles of magnesium. We end up with grams of magnesium. Here we go. Bust out the calculator. 0.942 times 10 divided by 0.08206 divided by 500 times 2 times 24.31. And lo and behold, we get 11.2 grams of magnesium at the end. So, lots of stuff we can do with this. Lots of stuff. I think what we'll do is we'll end here today. On Monday we will continue. We'll do a couple more examples of this. Actually, we'll do many more examples of this. I want to just kind of show you that we can do any pathway we want in this kind of chart here. We could start here and end up here if we wanted. Or let's say we start with volume of solution A and we end up with gas B. We could go this way too. Or we can go from grams to gas constants, or from gas constants to other gas constants. We can do all sorts of fun things. So we can start anywhere we want with A. We could end anywhere we want with B. We can go whatever kind of units we're dealing with, but the main thing in the middle is the reaction coefficients. That's the important part here. Everything else is kind of stuff we've learned and forgotten, but it's there somewhere maybe. But our reaction coefficients are now what we need to throw in here. So that's the only thing that's new this chapter. All right, so let's let this settle in over the weekend. I did put your redox homework up, so that is going to be due on Sunday. Your double displacement homework is also due Sunday, the one that I put up last week. I think there may also be a lab coming up as well. I don't remember, but Canvas will have all the due dates for those. I did activate your homework for this stoichiometry. It is due next weekend, so not this coming Sunday, but the next coming Saturday, because we will have our exam next Monday after that. So our exam will not be the 19th, it's going to be the 26th. So we are going to push our exam a little bit. It's just going to be on the chemical reactions and stoichiometry chapters, so 9 and 10 only. And so it's going to be all this fun stuff with reactions. So you can take a look at that. If you feel brave, you can go ahead and start the stoichiometry homework. Definitely does not hurt to do that. It's always good to practice. So yeah, I would definitely suggest getting on those. So, all right. If nothing else, I will see you next week. Next week we'll also do a review session on Thursday. So if you guys are having questions, throw them up in Discord for next Thursday, and we will do a review session then. So just don't forget about that. Okay? Alrighty then. With that, have a lovely weekend. Enjoy the wonderful weather. Take care.